From the air, Vaavu Atoll looks calm, a ring of coral, small islands, blue lagoons, narrow channels connecting the inner water to the open Indian Ocean. On a map, the entire structure appears almost simple, but underwater, Vaavu Atoll is not a flat ring. It is a moving system. Water is constantly being pushed through its channels. Currents accelerate along reef walls. Sand shifts, visibility changes. And a location that appears easy to understand from above can become completely different once a diver descends beneath the surface. That is the problem with maps. They show where things are. They do not always show what the water is doing. And in Vaavu Atoll, the moving water may be just as important as the rock, reef, and cave beneath it. This video is not another attempt to draw the exact shape of the fatal cave. No verified public survey has yet established every corridor and chamber. Instead, we are going to examine the larger environment surrounding the tragedy. What is an atoll? Why does Vaavu contain powerful channels? How can current change a diver's route without the diver immediately realizing it? And why can two maps of the same place both appear correct while giving a completely different impression of the danger? Vaavu is the administrative name commonly used for a region that includes Vaavu Atoll and the smaller Vaavu reef. Vaavu is shaped roughly like a diamond, with long reef edges and multiple openings connecting its inner lagoon with the open ocean. Those openings are known locally as kandus. A kandu is more than a gap in the reef. It is a water corridor. As tides change and monsoon-driven water moves around the islands, enormous volumes of water can flow through these channels. That movement creates some of the most exciting diving in the Maldives. It also creates some of the most demanding. Divers visit Vaavu because the channels attract marine life. Nutrients move through the passes. Sharks patrol the edges. Schools of fish gather where the current meets the reef. But the same water that attracts life can also change a dive very quickly. A map may show a channel as a fixed opening between two reef sections. Underwater, that channel may behave like a river. The center can move faster than the edges. Water can accelerate as it is squeezed through a narrow section. Eddies can form behind reef projections. A diver close to the wall may feel one direction of movement. A diver only several meters away may feel something stronger or slightly different. This makes an atoll dive difficult to represent on a simple screen. Most maps are designed to answer one question: where is the reef? But a diver needs answers to several more. Which way is the current moving? How fast is it? Is it entering or leaving the lagoon? Where does it accelerate? Where does it create shelter? Where are the drop-offs? And what happens beneath the depth contours that are not shown? A flat map cannot easily answer those questions. Imagine looking at Vaavu from directly above. You see the lagoon in the center. The Indian Ocean surrounds it. Channels cut through the reef rim. That tells you the horizontal layout. Now rotate the map and look from the side. The reef is no longer a thin line. It is a wall. The shallow top may begin near the surface. The outer edge can drop steeply into deeper water. Inside the channel, the bottom may slope, rise, or break into ledges and overhangs. A location that appeared to be a simple opening on the overhead map becomes a three-dimensional corridor. Now add current. The map is no longer showing a place. It is showing the container through which the water moves. This distinction matters because divers do not travel across maps. They travel through moving water. A dive team may descend at one point and expect to reach a reef feature directly below, but the current begins moving them sideways during the descent. The deeper they go, the less obvious that movement may feel. There are few fixed visual references in blue water. The divers may believe they are descending almost vertically. In reality, they may be drifting across the reef face. By the time the bottom or wall becomes visible, they may be tens of meters from the intended location. Vaavu's channels are famous for drift diving. During a controlled drift dive, the moving water does much of the work. Divers maintain position near the reef and allow the current to carry them along. That can feel effortless, But effortless movement creates its own danger. A diver may travel farther than expected without realizing how quickly the distance is increasing. Swimming back against the same current may be extremely difficult. If the planned exit point is missed, returning to it may not be possible. This becomes even more important near deep reef openings, overhangs, or caves. The current does not need to force a diver directly into an opening. It only needs to bring the team near it. Once the divers begin examining the feature, their attention shifts from the larger environment to the rock directly ahead. The current continues moving around them. A few seconds of observation can change the team's position. A slight correction can become a deeper descent. The diver may believe they are choosing the route. The water may already be influencing which route is easiest. We should be careful not to claim that current caused the fatal Vaavu cave incident. The official investigation has not established a complete public sequence, but understanding the atoll helps explain why a location cannot be judged from one diagram alone. One online map may show the cave entrance relative to the reef, another may show the chambers from the side, a third may reverse the image so that the entrance appears on the opposite side of the screen. All three could be attempts to show different perspectives. The problem begins when viewers assume that each drawing is an exact official survey. A map can be rotated, mirrored, simplified, or drawn without a compass direction. If north is not marked, left and right have no fixed meaning. A corridor shown moving left on one screen may be the same corridor shown moving right on another, because the illustrator is viewing it from the opposite direction. This does not automatically mean one map is false. It may mean the perspective changed. The same thing happens inside the cave. A passage viewed while entering may seem to curve right, turn around to leave, and it now appears to curve left. The rock did not move. The observer reversed direction. That sounds obvious on land. Inside a cave, under stress, and with reduced visibility, it becomes far more confusing. This is why map orientation matters. A useful technical diagram should identify north. It should show the direction of travel. It should distinguish a plan view from a side profile. It should label estimated distances and depths. And it should clearly state which features are confirmed and which are reconstructed. Without those labels, a dramatic illustration may look authoritative while hiding large uncertainties. There is another limitation. Most broad bathymetric maps do not show small caves or tunnels inside the reef. Bathymetry measures the shape of exposed underwater terrain. It can show reef slopes, lagoon depths, and larger channels. It cannot automatically reveal every enclosed passage beneath solid coral or rock. That requires direct cave surveying. Divers must physically enter the passage. They measure distance, depth, direction, and changes in elevation. They then build a survey from those measurements. A cave can therefore sit inside a well-mapped atoll while remaining poorly mapped itself. The atoll map and the cave map are not the same thing. The first describes the surrounding geography. The second describes an enclosed route hidden inside it. This is the original mapping lesson from Vaavu. The broad environment can be known while the most dangerous small feature remains uncertain. From a satellite, the reef rim may be visible. From a boat, the channel may be charted. From a dive computer, depth may be recorded precisely. Yet none of those tools alone can reveal the complete interior of an underwater cave. Each system sees a different part of reality. Satellite imagery sees the shallow surface and reef outline. Sonar sees exposed underwater terrain. A compass sees direction. A dive computer sees depth and time. A camera sees the scene in front of the diver. A guideline gives a physical route back. No single tool provides everything. Problems begin when one tool is expected to answer a question it was not designed to answer. A dive computer can say that a diver is at 55 meters. It cannot say which tunnel leads outside. A nautical chart can show the reef edge. It cannot show whether sediment is hiding an opening. A satellite image can show turquoise shallows. It cannot show current strength beneath the surface. This is why digital certainty can be misleading. The numbers may be accurate, the picture may be sharp, but the information can still be incomplete. Vaavu Atoll is especially useful for understanding this because the surface appearance is so deceptive. The water is clear, the islands look peaceful, the lagoon appears protected. But the atoll rim is a boundary between two enormous bodies of moving water. On one side is the open ocean. On the other is the inner lagoon. The channels connect them. As water levels and weather conditions change, the passes become the routes through which that water must travel. Narrower passages can increase current speed. Reef walls shape the flow. Corners produce turbulence. The underwater landscape controls the movement. A map may show the channel as empty blue space. In reality, that empty space contains force. Divers often describe current in terms of direction. Incoming current, outgoing current, but direction alone is not enough. The strength can vary with depth. Near the reef wall, friction can slow the water. Away from the wall, the flow may be faster. Behind an outcrop, a diver may find temporary shelter. Leave that shelter, and the full current returns. This creates a patchwork of conditions within a small area. A team can become stretched apart. The leading diver enters fast water first. The last diver remains in shelter for several more seconds. The gap widens. Lights become separated. Communication becomes harder. Now add depth. Gas consumption increases as pressure rises. A diver working against current breathes faster. A calm drift becomes physical effort. The pressure gauge falls more quickly. The current that looked like a navigation problem becomes a gas problem. Then it becomes a team problem. This is how hazards connect. The atoll does not need one dramatic trap. It only needs current, depth, terrain, and limited time to interact. The maps shown in videos often fail to communicate that interaction. They draw arrows to represent water movement. But an arrow looks stable. Real current changes. They draw a smooth reef wall. Real reef surfaces contain cuts, ledges, overhangs, and irregular slopes. They draw a cave entrance as a clean black opening. Real entrances may be partially concealed, angled, or difficult to recognize from certain positions. They draw the divers as dots moving in a straight line. Real divers rise, descend, drift sideways, stop, turn, and separate. A simple map is useful for explanation. It becomes dangerous only when we forget that it is simplified. That is why viewers are correct to question diagrams that keep changing. The honest answer is that no public video should claim to possess the perfect map unless it is based on a verified survey. The best creators can do is label the perspective, explain the uncertainty, and avoid presenting illustration as evidence. For commander puzzles, this also changes how we should discuss the tragedy. Instead of drawing another speculative tunnel, we can ask a larger technical question. What did the team know about the surrounding atoll? What were the tide and current conditions? Where was the planned entry? How far could they have drifted during descent? Was the cave entrance visible from the original target? Did the surrounding reef shape make the approach easier in one direction than the return? And did the boat's surface map reflect the environment the divers actually encountered below? Those questions require data that has not yet been released. But they are different from repeating the same cave diagram. They place the incident inside the larger moving geography of Vaavu. The atoll itself becomes part of the investigation. Not as a villain, not as a fictional abyss, but as a physical system that turns flat maps into incomplete stories. When investigators eventually release a verified reconstruction, the ideal presentation should contain several layers. First, an aerial map showing the atoll and channel. Second, a closer reef map showing the dive location. Third, a side profile showing depth. Fourth, a surveyed cave diagram. Fifth, current direction and estimated strength. Sixth, the synchronized dive computer profiles. Only then can the public see the complete relationship between the surface plan and the underwater route. Without those layers, arguments about whether the tunnel goes left or right may miss the larger issue. Left and right depend on viewpoint. Depth depends on the vertical profile. Current changes the route. And an atoll is not a flat ring. It is a three-dimensional structure filled with moving water. That is the most surprising truth about Vaavu. The map may be correct. The diver may still end up somewhere unexpected, because the map shows the reef. The current determines how the diver reaches it. 5 divers entered the water in Vaavu Atoll. The final investigation may focus on the cave, but the journey began in a channel system shaped by reef walls, tides, depth, and moving water. To understand the final route, investigators may need to reconstruct not only where the divers went inside the cave, but how they arrived at the entrance in the first place. That is the map we have not yet seen. Not another sketch of chambers, a complete environmental reconstruction. The atoll, the channel, the current, the descent, and the hidden transition from open water into an overhead environment. Until that exists, every map tells only part of the story. What should investigators release first? A verified cave survey? A map of the surrounding reef? The tide and current information? Or one synchronized reconstruction containing all of them? Tell me in the comments. And remember, a map shows the ocean's shape. It does not show the ocean standing still.